The direct shear test is not the only test that we do to measure shear strength, and another popular test is called the triaxial test. And the the triaxial test, sort of schematically, looks like this. I'm going to draw it in a rough way. We have a cylindrical sample, so the sample comes out of the sampling tube, usually, and it looks like that. And by, in a sense, putting a vertical load on it, we end up with a failure situation that looks approximately like this, whereby we create a shear plane. And so it doesn't, surprisingly, I mean, you can actually see this occur. So it looks a little bit odd, you might think at first, but this has been observed quite frequently. And so by, we create this vertical load, but we create a shear plane. So it's a shear test, even though it doesn't look like we are applying shear stresses. So, all right, this is sort of a rough picture. In more detail, I've got the test down here, and we have a cell around the soil sample. So here's my cylindrical sample, and what we do is the cell around the sample is filled with water, and that water is pressurized. Now what we do is this water here does not contact the soil because we have a membrane that separates and keeps the water from contacting the soil. And the only purpose of that water here is to pressurize the soil and create a confining stress on it. Now, the load P goes through a piston which contacts the top cap of the sample. Here I'm showing the bottom cap is a porous stone, and that allows water from the soil. So, frequently the soil itself is saturated, and when we apply, we do a couple things. We pressurize the cell and for a portion of the test, and then water can squeeze out of that soil and down through a valve that we have here. We can keep that valve open, and we are able to get pore pressure dissipation in the soil sample. So again, this is a more of a schematic of what we have. We've got the pressurized cell, we've got the membrane, we've got the porous stone, we have this valve, we have the load P, and that is approximately what the test looks like. The water is under a pressure that is chosen by us. We choose that pressure, and that pressure is going to impact the result of the test. So that cell pressure, we're going to use sigma cell for the cell pressure, and that plays an important role in our test results. Then we increase P until we get failure of the sample. So the failure of the sample looks something like that. Now, this valve, when the valve is open, what does it mean? That means U excess can dissipate. And we keep the valve open during the consolidation phase. Again, we have two phases, a consolidation phase and a shearing phase. And during the consolidation phase, we keep the valve open. If we're going to run an undrained test, a quick, fast test, total undrained fast, the valve is closed during the shearing phase, just to make sure we don't get any pore pressure dissipation, excess pore pressure dissipation. So as I said, there are two phases to the test. There's the consolidation phase, which is when we apply the cell pressure only, and we wait 24 hours or till the excess pore pressures have dissipated. That ends the first phase. The second phase is the shearing phase, where we apply P. And if we apply it quickly, it's undrained. If we apply the load slowly, or increase the load slowly, that is the drain phase. And of course, we leave the valve open and make sure that the excess pore pressures dissipate during shearing. So for a drain test, we leave the valve open. And I'll just mention, we can also measure U excess during shearing if we wish. So comparing the two tests, we have, for instance, the direct shear test and the triaxial test. So TX stands for triaxial, DS direct shear. And what we find, just to compare the two, we use P to consolidate our sample. And the consolidation stress is P over A. For the triaxial test, sigma cell is what consolidates the sample. For the direct shear test, our force F shears the sample. And in the triaxial test, the force P shears our sample. Now, if we look at the stresses in the triaxial test, this is the way they're typically drawn. So here's our soil sample, and during the consolidation phase, we just have the cell pressure acting all around our sample. So we consolidate the sample under sigma cell, and that acts in all directions. For the shearing phase, what do? Well, we already have our cell pressure, that's on it, which we had from, that's from there. And so that cell pressure acts, and then what we do is we increase our P, which gives us a stress P over A, right, because P is load, A is area. And we get we are going to call it a deviator stress, sigma deviator, which we're going to abbreviate sigma D. It's commonly called that, put it this way, that's just the name for it. So we have sigma D, it acts obviously on the top and the bottom, equal and opposite. And then what we're going to do, if you look at this, well, we can draw a Mohr circle for this. It goes back to, Mohr circle, which you're familiar with. Just to refresh your memory on Mohr circle, our Mohr circles will not be very complicated, but just remember how we plot up our circles here. So, in the most fundamental form of the Mohr circle, what we do, so if you remember these, we look at the stresses on one of the planes. We look at the stresses there and there, which are identical to the stresses there and there. So there's redundant information on this, if you remember. But if I look at this, I'm not going to go through it, but those two stresses are 1 and 3. And so we plot the 1, it's 1, 3. We plot the point 1, 3. Remember, our Mohr envelope is sigma and tau. Our Mohr circle is plotted on the axes sigma and tau. The other point here is, well, -5 for that one, -3 for that one. So I have -5, -3. And then we have these 2 points plotted, and what do? We draw a straight line between them. We get the center of the circle where it crosses the x-axis. We draw the circle like that. We get off from this plot the tau max. And if you remember, the whole point was of drawing this was that, in other words, we know the stresses on the vertical plane, which are 1, 3. That's why we write vertical plane. We know the stresses on the horizontal plane, -5, -3. That's on the horizontal plane, so we write horizontal. So we know the stresses on those planes, but, the purpose of drawing the Mohr circle is like, well, what's the stress on that plane? Or what's the stress on a plane here? Or a plane, or whatever plane we want is going to be represented by the coordinates of the different points on the Mohr circle. And so by drawing this Mohr circle, we've been able to find a tau max, which means there's some plane in here. I'm not going to go through there's some plane in here that has the maximum shear stress. And that's what we're interested in. In other words, if this were our soil sample and we were applying those stresses to our soil sample, we would have a plane somewhere that has our tau max, and that is where we're going to get our failure plane. So that's the basics. That's a little refresher on the Mohr circle, but for the triaxial test, things are much easier. We're going to have something that looks more like that, where we don't apply any shear stresses to these horizontal or vertical planes. Because in the triaxial test, notice when I go back to here's our triaxial test, we're not applying any shear stresses to the vertical or horizontal plane. By applying this vertical load here, yes, we get shear stresses on this plane here, but we don't directly apply shear stresses on either the vertical or horizontal plane. So we end up with this as our the stresses that we apply, and on the vertical stress is greater than our horizontal stress, for instance. So that is our basic stress configuration that we need to analyze, and it looks something like that. So instead of this is a square instead of a rectangle. That's the only difference, but it doesn't make any difference to our analysis. And in this case, our horizontal stress is less than our vertical stress. So this is somewhat typical of a triaxial test stress configuration. Now, the way that you learned it in your structural class, this represents compression, obviously. It's pushing toward the sample. This is also compression. It's pushing toward the sample. So the sign convention that you used in structural engineering was that compressive stresses are negative. And so if we do this analysis the way you do it in structural engineering, you would put on 2 points. Well, one would be, for this one, it's -12. And since there's no shear stress applied there, it's -12, 0. So it's very simple to plot. -12, 0, it's on the horizontal plane. That's what the horizontal means, not horizontal stress, it's the horizontal plane. And then we have -4, 0, so that's -4, 0. It's acting on the vertical plane. That's the vertical plane. So I have these 2 points. It's very simple. I connect them with a straight line. I get the center halfway between them. And then I draw my Mohr circle, and, it's pretty easy to get the radius. I get my tau max. There's my tau max. And, tau max equals the radius. Very easy to get. And the radius is simply the difference between the two divided by 2. So my radius is my y value. So my radius is 4. And so there's my tau max is 4. And that, if you figure this out, it acts on a 45-degree plane. So we are creating a tau max on the 45-degree plane. Now, in geotechnical engineering, we flip this around, and we call compressive stresses are positive. That's what we always do. So we have, so we reverse it a little bit. So if these are my stresses here, then it's easy to plot. I just look at one of them, and it's sigma cell 0. So there's 1 point. Sigma cell plus sigma deviator. Sigma cell plus sigma deviator, that's the other point. So I simply draw a line between them. I get the center. Well, I know that the radius is what? The radius, this radius is a sigma deviator. So if the the diameter is sigma deviator, if the diameter is sigma deviator, then the radius is sigma deviator of 2, and the radius is our tau max. So when I have this stress configuration, my tau max is simply the sigma deviator divided by 2. And that's what we're interested in getting, because that's the shear stress that we're applying. And remember, soils fail in shear. They're not steel. Steel fails in tension, for instance. Soils fail in shear, so we're always interested in the shear stresses. And to top it off, is something else that we do differently is we often just draw half a circle. So we have our sigma cell plus sigma deviator, and tau max sigma deviator over 2. So you will frequently see this. Compression is positive, and we only draw half a circle. So it's a little bit different from what you learned previously. Okay, so let's look at how we can analyze a particular situation where we have, again, I have 3 samples, A, B, and C, 5 meters, 10 meters, 15 meters. We have a clay with an OCR of 1.3, gamma saturated is 19.8, water tables at the surface. And we have these observed test results. So on A, we have that test result. On B, we have that test result. On C, we have that test result. Now, what are the tests? Well, this one's fast. It's an undrained test. So an undrained triaxial test. So these are all triaxial tests. And the way that we plot up the results, we plot sigma deviator versus epsilon, UXS versus epsilon. So it's more like the stress strain curve that we've seen before. It's a sigma epsilon. It's our, you've seen stress strain curves that look like that, and they look very similar. In addition, I have my cell pressure, which is 200 kilopascals in this particular case. We have 120 kilopascals at the peak. We have 80 kilopascals also at the peak for the UXS. So that's the information, and this is an undrained test. So we have UXS, it's an undrained test, we do it fast. Turn the valve closed. We've consolidated the sample. The cell pressure is what we consolidated to, 200 kilopascals. For the second test, well, again, it's a fast test. We didn't measure UXS, so we're missing that piece of information. In this case, our cell pressure was 20 kilopascals, and that's 36. And this one is, from 10 meters down, so B is 10 meters down. A was 5 meters down. So samples came from different places. For our last one, it's a slow test, so it's a drain test. Our cell pressure is 50 kilopascals, so we consolidated as 50 kilopascals. We got a sigma deviator at failure of 70. And we didn't measure U excess, but it's a drain test, so it should be 0. So we're going to take it as being 0. So with all that information, we want to find S sub U over sigma prime I versus OCR, which we've done before. We want C prime and phi prime. We want SU at 8 meters depth, so in here someplace. we don't have a sample at 8 meters depth, so we have to figure it out. This frequently happens. We can't, in real life, we can't get and test samples everywhere. Can't get samples at every depth. We can't test every depth. So what we have to do is we have to figure it out based on what we know about how soils behave to get the information at locations that we don't know. And we want to get tau FF under drained loading at 10 meters depth in situ. Now, at 10 meters depth, we do have a sample, but we didn't run a drain test, we ran an undrained test. So, again, we have to figure it out. What is the strength at 10 meters? And the way we define epsilon is delta H over H. Basically, H is the original height of the sample. And we created a table very similar to what we've already looked at. So we have tests A, B, and C. The sigma prime in situ, you can all get that at 5 meters. It's 5 times 19.8 minus 5 times 9.8 is 50. And similarly, that's 100 and 150. So you can all get that number. Our sigma prime P in situ, we were given an OCR of 1.3. From where do we get that? From consolidation tests, which I haven't shown the consolidation test, but they would come from consolidation tests. So we multiply 1.3 times the sigma prime in situ, and we get 65, 130, 195 for those. The sigma prime I is the sigma prime cell. The sigma prime cell we're given, 200, 20, 50. Okay, so our sigma prime P of the sample again, how do I get that? Well, it's again the greater of columns 2 and 3. So I look here, 200 is bigger than 65, 200. 130 is bigger than 20, 130. 195 is bigger than 50, 195. So remember, the sigma prime P of the sample is the greatest stress that sample has ever felt. And since we took our first sample and loaded up to 200, well, it's greater than what it felt in situ, 65. So that's why that number is 200, whereas for these, the greatest stress was what was in the ground in situ. Because in the lab, we didn't put that full stress on. Now, that could be deliberate, it could be by mistake, a lot of different things happen. So we just need to analyze the test properly. So we get our sigma prime P of our sample, and then what do we want? We want our OCR of our sample. And again, what's OCR? Sigma prime P over sigma prime I. So there's sigma prime P, there's sigma prime I. And so column 5 is column 4 divided by column 3. So we get the OCR of our sample, and that means what? We got a 1.0 for that one, 6.5, 3.98, so all different OCRs. Okay, so then, following through with what we had before, now we want to get tau FF. Well, tau FF is what? Well, it's sigma D, the deviator stress, divided by 2. The deviator stress at failure divided by 2, because of the Moore circle effect, which we just looked at. The tau max was the sigma deviator stress at failure divided by 2. So, we took everything, we divided by 2. So we looked at these peaks, 120, 36, 70, and we just took those and divided by 2. 120 divided by 2, 36 over 2, 70 over 2. The test type, well, the first 2 tests were undrained, they were fast. The last test was slow, so it was drained. So I can get my SU, but I can only get the SU again from the undrained test. So that's 60 and 18, which are just simply the tau FF. And then I get this SU over sigma prime I. Well, what is that? That's, got my SU. Oops. I've got my SUs. I've got my sigma prime I. I divide them out. So column 8 divided by column 3. So column 9 is column 8 divided by column 3. So I get 0.3 and 0.9. And then the last thing I want to get is sigma prime FF. which is the sigma prime cell at failure. So I have to take off the UXS if I've measured the UXS or I know the UXS. Well, for sample B, I don't know the UXS. We didn't measure it. See, we did. It was fast and it was not measured. So I know that there is an excess pore pressure, but I don't know what it is. So, oops, I can't use it. So it doesn't give me more information. On the other hand, this one's slow, so I know UXS is 0. So I know the UXS there. This one's fast, but I measured the UXS, so I got that one too. So I can only use the first and the third test, A and C. So this works out to 200 minus 80, 50 minus 0. And I get 120, I get 50. So, okay, so then what do I do with that information? Well, I plot it up on I can do my more circles. I'm plotting sigma prime versus tau. Well, what do I have to use? I've got to use my sigma prime FF. I'm interested in everything at failure. There's no point in plotting the circle at a time other than failure. So I have what? I've got my tau FF. Well, yeah. How do we get it? Well, we have, for instance, for sample C, my sigma prime FF is 50, so there's my 50. My sigma deviator at failure is, 70 here. And so I use the sigma deviator of 70, and I put on 50 plus 70 is 120. So that gives me, this is the circle for C. For the other one, by coincidence, that's 120, so that's also at that point. And then my sigma deviator is 120, that means the diameter of the circle is 120, and so I add that together, I get 240. So I can draw, so I've got this point, and then that point, and that point. So I get a circle here, and I get a circle here. I can draw them, and I know what the radius is, I know what the diameter is, I know where they're located and everything like that. That gives me, so I now have my two circles. So I've got that done. Now I'm going to get my sigma prime I versus OCR. Well, SU over sigma prime I versus OCR. Well, I've got my SU over sigma prime I right here. I have my OCRs right there. I take those values and I put them here. So I have 1.3. So 1.3. There's point A. For the other one, I've got 6.5.9. 6.5.9. That gives me point B. And then what I do is I draw a straight line between the two of them. And we will work with that straight line. So I've got all the information I can get from this. Now I have to work with it. And so let me just note the following. Now I want to look at sample A, for instance, and I'm going to plot it. This is another issue that you need to look at. This doesn't get us totally through the problem, but I want to observe this following thing. I can plot sigma versus tau, or I can plot sigma prime versus tau for the same, this is the same. That is the same. So I'm looking at sample A, but in the top one, just look at the difference if we plot total stress, sigma, and in the bottom one I'm plotting sigma prime. Well, what's the difference? Well, if I'm using total stresses, I just look here. And by looking there, I just see, I see 200, so that's 1 point, 200. I see 320, that's my other point, 320. And, if I notice that, what do I see? That's separated by 120. So I get a circle with a diameter of 120, and it begins at 200. If I plot up the effective stresses, so sigma prime, then what? Then my stress is what? 200 is the total stress, but the excess pore pressure is 80. So it's total minus pore pressure equals effective. So 200 minus 80 is 120. So I put 120 there. This one is 320, but again I have to subtract 80. So it's 320 minus 80, which is 240. So I put it there. So, and what do I end up with? Oh, it's the same diameter. So this will come into play later for us when we recognize that if I'm plotting the total stress Morse circle, it's the same diameter of circle. So essentially, in a sense, it's the same circle. But when I plot it, put this on sigma prime, as effective stress, it moves to the left. It's shifted to the left in amount equal to the excess pore pressure. So same circle, shifted to the left, depending on whether I plot the total stress or effective stress. So that's an observation we want to make to be able to use later. So, okay, so back to these are the effective stress, the effective stress Morse circles for our problem, and we just got done doing this. This is sample A here, 120 and 240 with the diameter of 120. So this is effective stress, which is what we're interested in. That's what we computed on our table. And then sample C, well, we got this circle, so it's a smaller circle. But now what we need to do is we draw our Mohr envelope, and how do we draw that? That Mohr envelope is tangent to these circles. That's how we draw it. And when we draw our Mohr envelope, we get the same thing, C prime and phi prime, which is what we want. Now the math is a little bit more complicated, but not very difficult. So I'm just going to lay out just a little bit of similar triangles. It's easy. So if we look down here, we're going to create two similar triangles. I'm going to take this line, I'm going to extend it all the way out, and I'm going to call that distance A. I don't know what distance A is, but we're going to find it. And I'm going to create two similar, I'm going to take this as a similar triangle to this triangle. So notice I start from the center of the circle and I draw to the tangent. And I know that a tangent is a right angle there. Center of the circle, draw to the tangent, right angle. So I have that. So, this big triangle is this here. This little triangle is this one here. And so I'm going to look down here, and I'm going to start to fill in what I know. Well, I know the radius of the circle. The diameter is 120, so the radius is 60. You can look through that and figure it out. I know that that value is 180. What does that mean? That means this distance here is 180. This distance here is 180. So the total distance here is 180 plus A. I don't know what A is, but I'm just calling it A. And Similarly, this distance here for the smaller triangle is 85 plus A. So, and I know the radius of that circle here is 35. I'm not going to go through that again. You can figure that out. So I end up with, using similar triangles, 85 plus A over 35, so that over that is going to be 180 plus A over 60. That over that. So I have similar triangles. I have, in this expression, I only have one unknown. The only unknown is A. I can solve for A. I get A is equal to 48. Then I'm going to use this little triangle here. If you can see that. And so now I've got another triangle here that I'm going to use. And this triangle here is here. So I know that this distance is A, that distance is C prime, and that distance is, or that angle is phi prime. So I'm going to use that as well as this triangle here. So what can I say? Let's look at this triangle here. So this distance is 85 plus A, and I know what A is. It's 48. That's 35. So I can see that the angle, so this angle right here, is, the arc sine of those two distances. So the arc sine of 35 over 85 plus A, I know what A is, I put it in as 48, and I get that angle is 15.2 degrees. Now that I know that angle is 15.2 degrees, I can use it over here. It's 15.2 degrees. I know what A is. That means I can get C prime. I know that the tangent of phi prime is C prime over A. So C prime is A tangent phi prime. I can plug in those values, and I get that, I guess I'm missing it. I don't see the value of C. So that value of C prime, then we can get, and let's just do that. So we have that so that means that C prime is going to be 48 times the tangent of 15.2, and so we get C prime is equal to 13.0, and the units we're working in, so I guess we've sort of dropped the units here, but we know that they're stress units, and if we did everything right, they're kilopascals. So they are 13.0 kilopascals. So we have solved the drained problem, and then we can look at, so what did we want? We wanted C prime and phi prime. That's what we wanted. So, we have our C prime here. We have our phi prime there. We wanted the drained failure envelope. A lot of work to get there, but we got there. For the undrained situation, we have the plot we've already made, and I'm not going to go through this, but again, we have 2 points. I want to write the equation of the straight line. I get the slope. I go y equals mx plus b, etc. I get an expression for this line, But now I want to know what is the value. Our in situ OCR was 1.3, which means x equals 1.3 in our equation. And we put it into that expression. And so our SU over sigma prime I is the y, because that's plotted on the y-axis. And we solve for y. And we get SU, so SU over sigma prime I is 0.109 OCR times plus 0.19. I plug in the 1.3, which is the in situ value. I get SU over sigma prime I is 0.33. So that is our value in situ for the OCR of 1.3. And then we wanted to know what is the tau FF, the undrained shear strength at 8 meters. So I use my soil profile. I already know what the sigma prime I there is, 80 kilopascals, because we believe we figured that out from over here. No, I guess we didn't. But we saw at 5 meters it was 50. At 10 meters it's 100. So it doesn't take much to figure out that it's 80 at 8 meters. So I simply take the SU over sigma prime I times the 80. I get 26.6 kilopascals. So that's the in situ strength of that material. Then I want to know the drain strength at 10 meters. So I have to figure out sigma prime I at 10 meters, which we've already done, is 100 kilopascals. But now I use the drained failure envelope. So this is for undrained, this is for drained. And when I use this, what do I need to do? I have written this is the way to do this, is I know my C prime, I know my phi prime, and this is simple. My sigma prime is 100 kilopascals, so I use that value. And I just want to know what is the y coordinate here. So this is the x coordinate is 100. The y coordinate is simply, so what do I draw here? There's my failure envelope. I know this intercept, so I'm just going to draw this rectangle for this portion. And then I have a triangle for this portion. This is obviously 13.1, and this is 100 tangent 15.2, so just from basic geometry. And I get 27.2 for that leg of the triangle. So my total is going to be the 13.1 plus the 27.2. I get 40.3 as my tau FF. So my summary, I have C prime and phi prime. My SU over sigma prime I in situ. My SU at 8 meters depth, 26.6. My tau FF drained at 10 meters, 40.3. And just let me say the difference, what you need to remember here. So they're very similar. They're almost identical. So we've done this twice now, but the difference in plotting the results from the direct shear test and the triaxial test is that for the direct shear test, we plot points. Same axes, sigma prime tau, sigma prime tau. But in the direct shear test, we just plot points and we draw a line through the points. That, is a little bit easier. For the triaxial test, I have to plot the circles. A little bit more complicated, and I draw my line that's tangent to the two circles. So from an analyzing the test standpoint, that is the difference in the way that we look at these two tests. Okay, I'm going to stop here.